Hello, everyone. Welcome to Science Systems and Applications Incorporated, also known by our acronym SSAI's second live podcast episode. I am your host, Jason Dietrich from the SSAI Communications Department. I hope that you all have had a great start to the 2024 new year. As always, it is grand to be at SSAI with our engineers, scientists, and technicians. I just wanted to thank you all so much for listening in to our conversation today. If you are curious about what we've been up to, please make sure that you follow us on each of our social media platforms, LinkedIn, Instagram, Facebook, and our brand new YouTube channel. Please also check out our website. We have job openings in a variety of different fields, and if you are passionate about science, exploration, and humankind, SSAI is the place for you. All the links for each of our social media handles will be provided right down below in the description of this video. Please check each of these links out and don't forget to like, share, subscribe, comment, and engage with us via your questions about anything SSAI is currently working on. All our scientists, engineers, and technicians are doing amazing work and contributing to missions that are occurring, like at NASA, among many others, to help benefit humankind. Speaking of SSAI engineers, we have two SSAI employees joining me today. I have Sabrina Sharmin and Leland Chemerys. Both of them are OCI instrument system engineers who work at the Goddard Space Flight Center. Thank you both so much for taking time out of your very busy schedules to talk with me today. How are you both doing today?
Doing great. Snowed in and doing great.
Yeah. Yeah, I was going to say, we're definitely snowed in, yes.
I'm doing great as well. A little bit of shoveling this morning, but everything's going well. Kids had a good time.
Oh, yeah, I was going to say, I've seen, some kids playing in the snow across the street at my neighbor's house. Absolutely. So, and it's a great day at SSAI, right?
Yep.
So, each of you have been associated with NASA's upcoming PACE mission. For those of you who might not know what PACE is, PACE stands for Plankton, Aerosol, Cloud, Ocean Ecosystem, and the NASA PACE mission represents a unique step towards an improved understanding of the Earth system by allowing an unprecedented insight into the ocean and its interaction with the atmosphere and climate. Of relevance will be its ocean color instrument, also known as OCI, which has the ability to detect ocean color at a stunning level of detail, thanks to its hyperspectral design. Ocean color is a fundamental quantity that enables scientists in different fields to infer crucial properties of the ocean. In remote sensing, an instrument measures a certain physical quantity within a given range of frequencies. The more frequencies, aka channels, the instruments can sense within that range, the more detail is given on the observed quantity. In this podcast, we want to showcase both Sabrina and Leland's role that they have played and will be playing in the upcoming PACE mission. In addition, we are going to have future podcast episodes highlighting many more SSAI scientists' contributions toward PACE and many other future missions. So now, I would like to ask each of you some questions in relation to your work. One at a time. The first question I wanted to ask was to please tell the audience a little bit about yourself and state your role associated with the upcoming PACE mission. Sabrina, would you mind starting us off?
Yeah, of course. Firstly, hi again, and hope all the listeners is having a great new year so far. I'm excited to be here with Jason on today's episode to bring OCI's engineering to the conversation. And as already mentioned, my name is Sabrina, and I am a systems engineer for the Ocean Color Instrument, or OCI, which is the primary instrument on the PACE Observatory. As my background, educationally, I'm an electrical engineer, and this is my very first NASA mission. I joined the OCI team almost 7 years ago now, and I have played at least 3 different roles over the years. I started off working with the optical system, ground systems equipment, which is the OGSE, as part of our pre-launch calibration team, helping with all the test setups and data analysis from all the GSE. Then I think I worked with the integration and testing team as a test conductor, writing and executing code for testing the instrument. And finally, I joined the systems team as the verification and validation lead that involved verifying and closing out a lot of requirements for this complex instrument. And right now, I'm also learning a lot about the commissioning operations and helping out with that, mainly from Leland, I would say, so that we can ensure the operations and health and functionality of OCI after launch. I think this might not make sense, but I feel like professionally I've grown and personally too, alongside the development of this instrument. So really excited for the launch, less than a month left.
Wow, that is absolutely incredible, Sabrina. And I was going to say your very first NASA mission. I just want to say, congratulations. And I'm sure it's very exciting. It's also a little bit nerve-wracking. I think, all of us, can certainly agree with that because we want the mission to be super, super successful. And I know it definitely will be with both you and Leland and all the other scientists, engineers, and technicians at SSAI. It's going to be an incredible launch. So I am really looking forward to it. So thank you so much for sharing a little bit about your background. Leland, would you mind telling the audience a little bit about yourself and stating your role associated with the upcoming PACE mission?
Yep, absolutely. So as mentioned, my name's Leland Chemerys. I've been working at Goddard Space Flight Center for almost 20 years now, so a little bit more of a veteran than Sabrina. I've been on the PACE mission specifically since 2016, so it's been a long road so far for me. I'm excited for the launch. I have a degree in engineering physics, which is sort of a space systems engineering degree is what it turned out to be as I was going through my undergrad. And I've also evolved in my role on the project as I've been here. I started in the early requirements development phase where we're defining exactly what we're going to test for the instrument to make sure that we're meeting the needs of the scientists. I worked on that aspect. I moved into more of an analysis role where I was assisting with performing the timing analysis to make sure all the elements of the instrument work together properly and all the data is collected when it needs to get collected. And then I moved more into the operations end of things. So if somebody asked you to make a new phone and it was a brand new phone, had no operating system, and you had to tell everybody how exactly it was going to work, that's sort of what I did for this new instrument, which is what Sabrina was mentioning. I became sort of the resident subject matter expert for how the instrument operates, which is rapidly becoming more important as we approach launch and get to see it work on orbit.
Wow, that's absolutely incredible, Leland. And I love your phone analogy, that you provided as well, because, in terms of, the technology and the operations aspect, that goes into it, it's very complex. And it requires a lot of work, a lot of editing, lots of trial and error. So, it definitely takes time. You have to make sure that exactly what you're doing with that. But that is absolutely incredible. Thank you both so much for introducing yourselves and sharing your role with the upcoming PACE mission. And I just wanted to say that PACE is not only exciting and innovative from what I've been reading, but it's also going to help revolutionize observations we get about planet Earth, and it's going to lead to many more scientific discoveries. The upcoming PACE mission has a variety of different applications. On the very first podcast episode, we spoke about the science behind PACE, and now I'm going to ask each of you to answer a few questions that are associated with the engineering and technology aspects surrounding the PACE mission. Leland, I'm going to start off with you by asking this question about the PACE mission. NASA's PACE mission incorporates state-of-the-art technologies to study Earth's oceans and atmosphere. How is the integration of advanced sensors and imaging technologies such as the Ocean Color Instrument, OCI, and the two polarimeters, HARP-2 and SPEX-1, posed unique engineering challenges?
So during the development, we really kept bumping up against the capabilities of CCD technology, which we're using in the OCI instrument. These particular CCD detectors produce a lot of data. So together, we have 2 of them, and together they generate about 1.7 gigabits of data per second. So the mission allows for OCI to only send about 40 megabits per second of data while it's collecting. So we had to come up with ways to reduce this data down and fit in the pipe that we were allowed, and to only keep the data that we absolutely need. We ended up using a form of compression called aggregation that gives some flexibility on how much resolution we can get out of a ground scene. So the CCD actually has pixels that will allow you to look at high resolution images on the ground. However, we start adding them up. So the design is for 1 square kilometer, but it has enough pixels to allow for higher resolution limits up to our data pipe. So as we aggregate, we add the pixels together. So the amount of data is reduced, but the representative ground scene is now larger and loses resolution. So we can play games with where we want to adjust this aggregation to focus on different parts of the ground or different parts of the wavelength range that we're interested in. So the operations team is able to command OCI to look at different parts of the telescope scan as it's scanning. We don't look when we're looking backwards. That's not interesting. So we only pay attention to the data when we're looking at Earth. And then also, like I said, we can vary the aggregation around the wavelength portions of interest so we can get as much resolution as possible. As they spoke about in the previous podcast, how the hyperspectral aspect of things allows you to see a lot more data. We can pick the ranges that are important. So as we collect the data volumes are high among all the instruments, including SPEX-1, which is actually contributed by our partners in the Netherlands. They provided that instrument to the PACE mission. And HARP-2, which was designed and developed by the University of Maryland, Baltimore campus, which is local to us here, where the Greenbelt Goddard Space Flight Center campus is. So the flow of all this data needs to be managed to allow for the maximum amount of science collection. So for flight operations, the data ingest is staggered over the orbit. While we're looking at the Earth, OCI and SPEX send their data to the onboard storage in real time, while HARP stores theirs internally and then forwards it to the onboard data on the backside of the orbit, so they can maximize the amount of science collection. Then when all this is possible, we transmit this data back to Earth via ground station. So these were some of the challenges that we encountered while we were trying to develop this mission with all these instruments.
Wow, that's absolutely, incredible. And, engineering, without a doubt, it definitely presents, some unique design challenges. And, Leland, since you spoke about some challenges, could you elaborate on the innovative engineering design solutions that have been implemented on PACE to ensure the seamless functioning of these instruments in the harsh space environment?
Absolutely. So one of the many harsh aspects of spaceflight is the radiation environment. So here on the ground, we're largely protected by the magnetic field of Earth, and not just us, but also our electronics are protected. So everyone enjoys when manufacturers can make things smaller and squeeze more features into their phone. But as those electronics get smaller, they become more vulnerable to energetic particles that are flying around in space. These particles can actually enter the components and permanently damage them, making them inoperable. So it would effectively, that would be the end of science for OCI. As a result, most spaceflight electrical components are very large and heavy. So it makes them more robust, but less capable and harder to actually get to space. Because every ounce that you have that you're trying to send to space is very expensive fuel-wise. So everything needs to be small. The development team for OCI could not actually find a viable space-rated analog-to-digital converter, which is the component that takes the voltage measurement from the CCD and converts it to a digital number so we can interpret it for science. We couldn't find one that would meet our design requirements that was space-rated. So we found some decently robust commercial parts that were good candidates, and we had to develop our own dedicated test campaign to see if they could survive the radiation environment. Fortunately, they did. They did well in testing and are going to fly in about a month, as we mentioned. And this vendor that we purchased these components from actually performed some additional testing and is now marketing those components as space rated, allowing even more advancements in space technology, as now that's available for the development of more instruments.
Wow, I was going to say that's absolutely incredible. I'm glad that you guys were able to find, a vendor that can help you in that aspect. And as was mentioned before, the engineering and technology design aspect of the PACE instrument, there's a lot of work that goes into it, a lot of trial and error. So thank you so much, Leland, for sharing some more information in relation to the engineering obstacles and also the unique design solutions that you have implemented. That's incredible. And again, like I said, with both of you and your teams had many trials, errors, triumphs, and setbacks. But throughout my experiences in engineering, science, and STEM in general, you learn either way. And that is the benefit of being an engineer. And it all comes down to the engineering design process and the steps of the scientific method. And that takes me back to middle school when I learned the scientific method, which seemed like ages ago. So,
Same.
But if, no offense to you both. But if you get an idea, it's very important to try it out and to make sure you're following the appropriate steps correctly. And if it doesn't work, keep trying. Don't give up. So in relation to PACE, I wanted to follow up with you on the calibration and analysis associated with PACE. And Sabrina, I am going to turn these questions over to you. My first question is, can you explain to the audience the calibration that is used for PACE? What does it mean, and what is the importance of it as it ties to the PACE mission?
Yeah, of course. And we touched a little bit on the technological challenges that we faced with OCI. So just wanted to reiterate the fact that OCI is setting out to do that has something that hasn't been done before, and to answer science questions that we don't have answers to, mainly through its hyperspectral aspect. So that, along with the fact that ocean color applications require a very high degree of radiometric accuracy, that led to us having very stringent science requirements. So what happens when these requirements are very strict is that we have to ensure that the data we're providing is reliable. So for this reason, OCI has put a very considerable effort in investing in the planning of the pre-launch calibration campaign of this entire instrument, of the pre-launch as well as on-orbit calibration capabilities, so that we can meet all these stringent performance and uncertainty requirements that we have. So just to give a little bit of context, calibration of a remote sensing instrument is a crucial process that is basically ensures the accuracy and the reliability of the data collected. It involves testing to adjust and validate the instrument's measurements against known standards so that we are able to correct it. So our entire calibration campaign, for example, was run to derive 5+ coefficients for the different parameters of our calibration equation. So there's different types of calibration, just for context, radiometric calibration that adjusts an instrument's response to different levels of radiance or reflectance to ensure that we're giving the correct, accurate quantification of radiometric data, spatial calibration that corrects for any kind of geometric distortions in the art scene that we'll be seeing, and then temporal calibration that addresses variations that we might see in the detectors of the instrument over time. So for remote sensing, these instruments have specific parameters that need calibration, such as gain, linearity, spectral response, spatial resolution. So each of these must be adjusted to optimize the instrument's performance. So for OCI in particular, we have the in-flight calibration and pre-flight calibration. So I can go into a little bit more in depth of each of them. So pre-flight calibration, as the name suggests, is basically conducted before the instrument is launched, and it involved a comprehensive testing and adjustments to ensure the accurate performance in space. The main purpose was that so that we can test all these things to verify that the performance is okay relative to the requirements that was set by science to us. So I think this calibration campaign is when I mentioned I joined 7 years ago. It has been in the plans since then. We have different kinds of test configurations. Unfortunately, I don't think I would have time to go through all of them, but we verified 53 instrument level performance requirements with the ground support equipment that involved different kinds of things like broadband light sources for signal to noise ratios. That was like, we have very high signal to noise ratio requirements, integrating spheres that were also some of them were thermal vacuum compatible, so they went inside the thermal vacuum chamber when we did testing. We had collimated light sources for spatial characterization that projected art scenes into the instrument. We had, I think it deserves to be called out, we had a monochromatic tunable laser system. It's called the Glamour laser system. So being a hyperspectral radiometer, spectral characterization of OCI is of great importance. And the main source for this spectral characterization was our Goddard laser for absolute measurement of radiance, also known as Glamour. So it's a tunable laser system that provides monochromatic or basically single wavelength radiance of a wide range of wavelengths at a 0.1 nanometer resolution. And this table, if you ever get a chance to Google this, it looks like a table from like a, science fiction movie. It's very cool to look at and very, very complex. So that's why I went to do a little bit more depth into it. And other than that, we also have in-flight calibration after pre-launch calibration. So we have so this is while the instrument is operating in space. We have a vicarious calibration campaign that involves comparison of ground measurements made by vicarious calibration teams on Earth, and then we have onboard calibration systems that involves solar and lunar calibration. So we have solar diffusers that looks at the sun and basically looks for changes in radiometric sensitivities of OCI over time, so we can compare it to the first measurement and then trend it. We also have independent lunar radiance calibrations, so that's going to be for long-term trending. So overall, basically, the engineering team really tried their best to enable the scientists and researchers to make meaningful interpretations of the data that we're going to get from OCI.
Wow, that's just absolutely incredible. And, I was going to say, I'll have to check out that table as well, Glamour, in relation to like a sci-fi movie, like you said, Sabrina. I'm definitely very curious to see that. Would you say that's like Back to the Future sci-fi, or is it like a totally different movie, would you say?
You should just Google it, and I would let you interpret it yourself.
Oh, okay. All right. Well, we can, certainly do that. And, we can ask, the audience, the listeners, and the viewers, to do it yourselves. We'd love to hear, some of your observations as well, including, some of your questions about that as well. And Leland and Sabrina can, certainly chime in and, answer any questions that is needed. So excellent idea, Sabrina. So looking forward to seeing some of the audience comments with that. Again, it is just, this is all amazing. And for me, this is why I got into STEM, because it provides multiple different highways of opportunity. There's so much that you can do. And in this case, you both get to design and interact with many different cool instruments. And based on my STEM experiences, I've learned that the design aspect is very important as an engineer. But to execute that idea, you need a team. And interdisciplinary collaboration is key. PACE brings together various scientific disciplines, including oceanography, atmospheric science, and environmental monitoring. Sabrina and Leland, I want to ask each of you one final question based on your work with the PACE mission. And Leland, I'm going to start off with you by asking you this question. In relation to PACE, how has the collaborative nature of the PACE mission influenced the design and implementation of its technology?
So in order to bring these groups together, we really need to satisfy all of the science communities that are supporting this project. So as a result, though, it did create some challenges. But as spaceflight programs can be very expensive, it's important to bring these groups together and do what we can to try and keep those costs down and have multi-purpose missions, which is what this is. So a significant challenge of this particular mission is the large dynamic range that was required of OCI. So dynamic range is basically the difference in intensity between the darkest and the brightest scenes that you have to look at. So if you look at like an image of Earth that you can find on the internet, the darkest features are often the oceans and the brightest are the clouds. And OCI has to look at both of these. So C is the cloud, or C in PACE is for the cloud community. These two groups plan on using the data acquired from OCI. Therefore, we had to design a system that would provide enough accuracy, as Sabrina was talking to, at the lowest available signals, yet not add so much gain to boost that signal to a point where the instrument would effectively be blinded for the very bright clouds. So we were very much threading the needle on what we were able to accomplish. So throughout this whole program, we were modeling and iterating and affecting the design in certain ways to make sure that we could meet all of these requirements. There were some areas where we had to compromise to give the ocean community priority with certain wavelengths where the instrument is effectively blinded when looking at clouds. But we were able to limit it to a region of the spectrum that doesn't really provide additional insight to the cloud community. So we're able to bring these groups together and get a data set that they can all be happy with. In the past, for some of the other missions, sometimes there were compromises were such that it was difficult for them to all use the data. But we're hoping that we have answered the mail for everybody here and we can really provide the best data set to all of these different science communities.
Yeah, that's absolutely wonderful. And, again, there's, various viewpoints and that you have to consider throughout, many different areas of, the scientific community. Like you said, Leland, it's incredibly important, to do and to take all perspectives into account because, not one person knows everything. Somebody else might know something that you might not. And, that's okay. That's why you have to work together as a team. As we say, it takes a village to raise a village, right? So that is, I've heard that quote all the time, from my parents. And it definitely applies, to PACE for sure and many other, future missions. So thank you very much for that. Sabrina, I wanted to ask you, can you discuss specific examples of interdisciplinary collaboration that have shaped the PACE mission? And can you highlight the benefits of bringing together experts from diverse fields to address complex challenges in Earth observation and climate science?
Sure. I think I'm going to go along with what Leland already touched on. I think the most remarkable interdisciplinary collaboration was for this mission is between the ocean scientists and the atmospheric scientists. So one of our main science goals for PACE, one of the main 4 science goals that PACE has set out to achieve is that improve our understanding of how aerosols influence ocean ecosystems and biogeochemical cycles and how ocean biogeochemical and photochemical processes affect the atmosphere. So by having both a highly advanced hyperspectral radiometer, which is OCI, and the complementary to polarimeters, this mission is able to give us new insights, not only on not only the ocean or the atmosphere separately, but insights into the integrated relationships among the ocean, atmosphere, and the biosphere, right? So the polarimeters achieve atmospheric goals on their own rights, but however, if you think about the fact that when ocean color instruments look down on Earth, almost 90% of we see the top of the atmosphere radiances. So almost 90% is through a veil of the atmosphere. So we can appreciate that the polarimeters are on the same observatory, which greatly complements OCI's data to improve atmospheric model corrections as well. So basically, this knowledge will play a pivotal role in enhancing our capability to model and forecast alterations in the Earth's climate. And then it's also essential to understand the health of the ocean, how it's related to that of, the state of air particles and clouds, for all sorts of scientific benefits. So PACE will definitely significantly advance our study of, our ocean atmosphere and their interactions.
Wow, that is just absolutely fantastic. I've just learned, so much more about the upcoming PACE mission. And Sabrina and Leland, I just wanted to thank you both again so much for joining me today to talk about the exciting upcoming PACE mission. You both are truly rockstar engineers who are making an impact and difference globally. And everybody is going to be very excited when this mission launches. I know I am. At SSAI, we believe the best way to obtain knowledge is to pass it on. So, again, for those of you who are curious about what SSAI has been up to, please make sure that you follow us on each of our social media platforms: LinkedIn, Instagram, Facebook, and our brand new YouTube channel. Please also check out our website so you can, again, stay up to date on PACE and other missions that SSAI supports. We have job openings in a variety of different fields, and if you are passionate about science, exploration, and humankind, SSAI is the place for you. In addition, if you want to learn more about PACE, please check out the link in the video description below for more information. Also, be sure to engage with us via social media with your questions and comments about this podcast and any additional future episodes that we do. We want to hear from you. Your voice and ideas matter. Thank you to those of you who already subscribed to our YouTube channel and have followed us on our social media. Please continue to like, share, and subscribe to each of our social media platforms to see all the global STEM initiatives SSAI is involved in. Again, I am your host, Jason Dietrich, SSAI's Communications Department member, and I wanted to thank you all so much again for joining. I hope that you have a wonderful rest of the day and be on the lookout for our next podcast episode. Until next time, everyone, cheers.